everyone. So I've made some changes to the online notes in the light of a couple of things. There was a question about how to look at the... Can you hear an echo in here? Can you hear me okay? Maybe it's this. Should be off. Is that one muted? Ah, there we are. That should be better, maybe. Okay, should be right. How's that? Oh, that's better. Okay, so I made a couple of changes to the notes online. The first thing was about this derivation of the expression for the real and the imaginary part of the refractive index. Okay, and one thing I noticed was I think I had a plus instead of a minus sign there. Okay, you will see both ways round written, but I've explicitly defined for the susceptibility, which is the equivalent calculation. I've shown you explicitly how you do that calculation, and you can practice that in example sheet 3, which is coming out in the next few days. Okay, so so you can have a practice just to make sure you can do that. The thing to note is this factor I and what happens to it. You should get cancelling terms, and you should get the real part and the imaginary part of the susceptibility as shown there. Okay. Right, so have a practice of doing that. And there are 3 equivalent calculations, one for the susceptibility, one for the permittivity. You just add 1 to everything. Right? And the key thing to watch out for is you'll see the complex part of the susceptibility either defined as minus I chi I or plus. Okay? And obviously it's up to you to work out which way around you do that minus sign, whether you put it into the definition or whether you put it into the attenuation part. Right, you'll see both ways written down. It's just something you have to watch out for. Okay. The other thing I've done is a bit later on, and I'll show this a bit later. I've added in where did I put it now? I've added an extra example. Where did I put it? Did I put it there? Ah, yeah. I put a bit more in about the plasma frequencies, which we'll come on to later. Okay, so I'm linking the scattering and the plasma frequency stuff a bit more. Okay, so that's what's happened to the notes. So just do download the updated ones. Okay. Okay. So where were we? We left it last on Monday. God, each week seems like a long week this semester, doesn't it? Oh, it's reading week next week, right? So no lectures. Okay. So we left it by talking about the fact the atoms would respond to an incoming plane wave. And that would give rise to both an absorption of the energy from the incident wave and would also give rise to a radiated component, which we now recognise as being what scattering is. So scattering, in our classical picture, scattering is the same thing as the re-radiation of the incoming part of an electromagnetic wave. And we have kind of ignored the relationship between the power in the scattered radiation and the power in the incoming radiation. Clearly there must be a conservation of energy that goes on there. So if we use we assume that the scattered radiation component is small in comparison to the incident plane wave, we can make an approximation where we can say in each particular distance travelled, we will reduce the intensity a little bit from the incident plane wave, and we can keep track of the energy that way. Okay? We do wonder whether the absorption of the electrons, the absorption by the electrons of the energy of that plane wave, that was our complex part of the refractive index and the complex part of the permittivity, whether that is somehow related to the radiation resistance. We're going to leave that aside for now, but it's an interesting thing to start thinking about. Now, the other thing we did is, remember, we did that approximation. We did the approximation that to work out the refractive indices, we made the approximation that the susceptibilities were small, so we could do that approximation of the square root. All right. Now, we should really think about how we should modify that understanding in a dense material where we may have a significant amount of polarization. Okay, and this is conceptually can be a little tricky, so we'll go through that derivation step by step. Okay? So we said in a gas, okay, that the electric susceptibility was much less than 1, both the real and the imaginary parts, and therefore there's not much polarization. Okay, in other words, a little bit like our radiative case above, what we're saying is the effect on the electric field from the things which are being polarized is a small component of the electric field in total. That's what we can say about a gas. Okay? Okay. So in a gas, the electric field seen by each atom is basically the external applied electric field, which you see in this case comes from the electromagnetic wave. Okay? However, but in a solid or a liquid, okay, for these purposes they are basically the same. It's a higher density material. There is a polarization, by which we mean a significant polarization, due to this from the external EM field. Okay? Okay, so of course external fields don't have to be electromagnetic, they could be static. Okay? But here we're thinking about the external electromagnetic field. So we imagine, therefore, the electric field at each atom is lower. We'll see what that means by means of a careful diagram. And we do have to be quite careful. Okay. So let's think of the local field around each atom. Let's think about the local field at each atom. And don't worry if you find this a bit tricky to work through conceptually. I do too every time I do it. Okay, so I'll try and draw the picture in a careful way. So here is our atom, right? And we imagine, due to the polarization, it has some kind of dipole moment. Right? So you know what that means, right? We have some displaced electron. Okay? And that is due to the passage of our electromagnetic wave. Now remember we said we could write down the total polarization in the material in the following way, where this is the way we define the electric susceptibility, right? We have the electric field. Oh, I'm sorry. There you go. Let me zoom that out a bit. Sorry. There you go. Okay. Okay, so we've got the electric field and we have the polarization. We've tied those together. Now, the dipole moment P, which that atom has, can be written down in another way, which is equal to some value alpha times whatever the local electric field is. Okay? So the polarization of all the other atoms is lowering the field seen by this atom. Okay? So this value alpha is another property of the material. We'll call that the polarizability. So clearly we're going to be relating these various numbers together. So when we had the susceptibility and the permittivity, we now have the polarizability. Now, this is the tricky bit, okay? Let's imagine a small region, a small vicinity around one of the atoms that's being polarized, and we'll give it some kind of characteristic size. So in the vicinity, okay, is a sphere, okay, of radius r. Right? Okay? And we're going to write down that the total electric field in the vicinity of that atom, E, is equal to the local electric field, okay, plus the electric field caused by the atom itself. That's the extra bit. Okay. Okay. Now, how are we going to separate out those bits? You have to look at this a couple of times to get it. All right, okay. So have a look at this and then read through notes. I'm going to sketch it out. You'll have to read it again. Okay. Now, let's write down the electric field from the atom. Well, that's generated by the atom's own polarization. So it has whatever the polarization is. Okay, the dipole moment is. Sorry, and that goes as 1 over 4 pi epsilon naught r cubed, because it's the dipole. Okay? And the total electric field is equal to, the apparent electric field, that's the one that's appearing in the formula up here, okay, is equal to the local electric field that's causing the polarization, that's from the other atoms. Take away what's happening locally due to the field from that dipole moment, okay, which is that again. All right? So of course I can relate the polarizability to the local electric field. That's what, yeah. So I can rewrite that. It looks like a cheat, but it's not. It's just that. Okay, so I can rewrite the total electric field in terms of the local electric field. Okay. Right. Now, the number density of these little vicinities is n equals 1 over the volume of that little sphere. Okay? Okay. So now I can relate the number density of the atoms to that size r. So we say how big is a size r for a particular number density of atoms is equal to 3 over 4 pi epsilon naught r cubed. Okay. So what? Well, we did know, because it's our definition of what polarization is. See how it looks circular, doesn't it? But it's not. Okay. The total polarization, as we defined it up here, remember we defined the polarization as due to some externally applied field, right? And now we're saying, if this is our externally applied field, how to relate it to the local field? We have to subtract a bit because there's a polarization near to the atom. Okay. But we still have this relationship between the polarization, the macroscopic polarization, and that applied electric field. Well, we know that must be equal to n times p, doesn't it? Right? So, we now know that the total polarization must also be equal to n alpha e local. Okay? Seems like a cheat, don't it? So let's just look at it one more time. What we've said is we have an externally applied electric field. It creates a dipole moment. The dipole moment, that gives rise to a small electric field in the vicinity of each one of the atoms, and that means that I can describe the applied electric field in terms of the local electric field and this polarization part, this dipole moment part. And using that concept and knowing that the number density atoms can be related to what this vicinity scale is, I can relate the macroscopic polarization to this polarizability. Okay? So what I can do now is I can compare those parts. I can compare the polarization, which is epsilon naught chi e. I can now relate it to the polarizability. So I've made that a bigger alpha. So I can relate this macroscopic susceptibility to the microscopic polarizability. Okay, so it's got a macroscopic and microscopic properties of the material. Now I can rearrange it because I can put in this term up here, and if you look carefully, you can show to yourself. I can write down this. Okay, I can rewrite the applied electric field in terms of the local electric field as so, okay, like so. Okay, so I've just replaced that left-hand term, and of course the right-hand side stays the same. Now obviously I can now get rid of E local, that can disappear. Right. What does that mean? That means I can now write down the electric susceptibility in terms of the polarizability and number density of the atoms, okay, some scaling factor, and actually I need to include it at the bottom as well. So that is a way of saying if I know the polarizability and I know the number density, I can work out the susceptibility. Really, it's done the other way around. Okay, you measure the susceptibility, you work out what the polarizability has to be. And obviously, the susceptibility is equal to the permittivity take away 1. The relative permittivity, of course. Okay. Now, just show it to yourself that have a look at the notes, see if you can just work through those steps one more time, okay? And you'll convince yourself that it does work. We're just going to rearrange this expression into its common form. This can be rearranged. That's better. Okay. This can be rearranged to give the polarizability in terms of the number density and the permittivity. Okay, so rather than writing it down in terms of the susceptibility, we know the susceptibility is basically the same thing as the permittivity with a difference of 1. Okay. So this is the Clausius-Mozzotti. I think that's 2 S's, or is it 1 S? Yeah, Clausius-Mozzotti relation. Okay. That's one way of writing it. Okay, so that's one way you'll see in the books. And you can rearrange that, if you wish, to another equivalent expression, which is a way of relating the permittivity and the susceptibility, okay, as so, like so. Okay. So what? Well, we can relate these two properties together, which is nice. That's one reason. What's that gone? What happened here? Ah. That's weird. Okay. That's weird. Look at my... There we go. Okay. That's better, right? Now, remember that when we were writing down the polarization of a material under the action of an oscillating electric field, we had an expression of this form. Okay? So just to recap, we had atoms, each of which had a number density Ni. Okay, and we saw there were different ways we could write this down. We could write it down in terms of polarization, susceptibility, and so on. Each one of those, we need to say that we were adding up for each of their natural frequencies, and omega here is the applied frequency. We could write down this polarization in terms of these two properties, the natural frequency and this damping constant gamma I. And remember, this is P as a function of T for a given amplitude of electric field which is oscillating at some frequency omega. Okay. Well, this expression on the left is now just the same thing as we just calculated on the right. This is chi of 1 plus chi e. Okay, so that's the reason why we did that. Sorry, that should be a minus sign. That's a minus, I'm sorry, that's a minus sign. 1 minus chi e over 3 epsilon naught e naught to the e omega t. Okay. What does that mean? That means, remember that we could get the real and complex parts. That's what we did last time. We can get the real and the complex parts of epsilon r by knowing Ni, omega I, and gamma I. Remember, that's what we started this morning talking about, and we did it on Monday. And we also remember right, that n squared is equal to epsilon r for our non-magnetic material. So we can recast our expression above. So epsilon r has got a relationship with n. We can recast our expression above in another form, n squared minus 1 over n squared plus 2. A little bit of algebra, but you can see where it's coming from. Equal to n alpha over 3 epsilon naught. Okay? So these are two ways of relating microscopic and macroscopic properties together, which I think is pretty cool, right? We can say, and above, that we say that the polarization properties and the electrical properties of material are brought about by the microscopic polarizability. But probably more interestingly, we see that the refractive index of a dielectric material is determined by the number density of the atoms and the polarizability of those atoms. Okay? And this is called, when we say there's different Lorentzes, well, this one's probably the most annoying one because it actually is both of them in it. It's called the Lorentz equation. And you try finding, you can imagine these get misspelled all the time. So sometimes with 2 T's, sometimes with no T's at all, sometimes backwards, I don't know. I think this is the right way around. I don't know which Lorentz has got priority, who knows, okay? But it's called the Lorentz equation of some kind, but they should be spelled differently, okay? Now the other thing you should watch out for here is you in some of the older textbooks, do watch out that when you switch from SI to CGS units, which you do occasionally, right? I know you lot are not yet happy with using CGS as a matter of course. You will be later, right? But when you switch from SI to CGS, you will find in this particular expression that 4 pi will be substituted for 1 over epsilon naught. So if you see the Lorentz relation in older textbooks and a 4 pi appears on the top and it doesn't have an epsilon naught on the bottom, that's what's going on, okay? I'm going to do SI here, but I'm just pointing that out in case it makes you unhappy when you see it, which it probably would do, wouldn't it? Okay. So that's dielectrics. So what have we done? We've shown the polarization properties can allow you to calculate, in broad terms, the attenuation of signals, okay? In principle, electromagnetic waves, but we'll look at signals in general a little bit later on. We've shown how the optical properties and the electrical properties of a dielectric are the same thing, and that's a very important thing to recognize. Okay. So that's that. That was dielectrics. Now we'll look at conductors, which are actually, I think, more interesting. So look at conductors. Right. Do you want to slide it up there? Have you got everything down? Yeah. It's all in the online notes anyway. So, waves in conductors. Okay. So we remind ourselves, what is a conductor? Well, let's say a metallic conductor, because that's what we're most familiar with, right? The atoms contribute, usually one each, yeah? They contribute electrons into a conduction band, as we know. Okay. And because the electrons are effectively unbound, this constitutes a gas of effectively free electrons. And we immediately see that there must be a relationship between the electrons in a metal and the properties of electrons in a neutral plasma, as we shall see later. So whenever we say metals, we will say equivalently, it's like a plasma. So under the action of an electric field, we know full well, don't we, that there will be a current. And the current will be finite because the electrons do not acquire well, they certainly don't go up to the speed of light, do they? They go a lot slower than that, right? They have a much lower average velocity, which we know to be the drift velocity. And therefore we can relate the current to the electric field, and there must be some proportion, some constant proportionality, our conductivity, which we again recognize if it's an oscillating electric field, will depend on the frequency of that oscillation. Okay. And we remind ourselves that in all the situations so far, we had this dispersion relation. So one more time, the dispersion relation allows us to relate the frequency of that oscillation, omega, to the wavelength of the wave that it results in the electric magnetic wave as it traverses the medium, whatever that medium is. Okay. And we saw that we could write that down. You immediately see here that obviously there's a problem with the square roots there, but we could write down the total wave number, 2 pi over lambda, as being a real part and an imaginary part. Remembering that I will try to write all the time minus, but sometimes we see it written down as plus. Okay. So clearly the absorptive part, the attenuation of the electric field, comes from the complex part of that expression. Right. Now, remember we divided up our materials into non-conducting and conducting. So we had the dielectric. Now in our conductors we're going to look at two situations for conductors. We're going to separate those out. Okay? And it might seem to be an oxymoron, but the first thing we're going to say is it's a conductor, but it's not a good conductor. All right? I know it seems a bit back to front, but there we are. So what do we mean by a poor conductor? Well, what is a condition for being a poor conductor? Well, it's clearly that the conductivity is small, but still large enough. Well, we still have free electrons, but the conductivity is small. And you can see that the important thing here is this ratio in this term. That's going to allow us to do some approximations. So our condition is clearly that sigma over omega epsilon r epsilon naught is much less than 1, which means the right-hand term is small. Okay? Can we think of an example of a poor conductor? Yeah, graphite. Let's say carbon. Just to put some numbers on. I like to do numbers occasionally. I've tried to put, you'll notice there's boxed examples in the online notes. Do have a look at them and see if you can calculate the various terms. At this point in the course, what I like to do is start picking up your calculators, as well as doing the derivations, start calculating numbers so you can calculate all the numbers repeatedly and reliably. You will need this in the examination. Okay. So in carbon, the conductivity is something like 3 times 10 to the 4 per ohm per meter, okay, for the typical frequencies we're thinking about, which are going to be sort of optical ones, okay, and that means this condition about it being a poor conductor applies when omega over 2 pi, that's the frequency, right, is greater than something like 10 to the 15 hertz. Okay? So first calculation I want you to go away and do is calculate what that wavelength is. Just make sure you can do that reliably. Okay? It's going to be optical-ish, isn't it? So, in this situation, clearly, here we can write our beloved approximation that 1 plus x to the half is about 1 plus x over 2, as we've done before. So now we can write an approximation for k. K becomes omega over c. We have that square root epsilon r mu r. That's our velocity term, isn't it? Yeah. So in a vacuum, we've just got that. Without a vacuum, we have that. We modify the velocity. Okay. But now we've got this extra bit, which is the conductivity part, where we now expect there to be absorption. So of course we can now immediately match those two terms, the real and the imaginary terms, to work out what the absorption is going to look like. So the interesting bit really that's new is this size ki. Let's find out the size of it. Okay. If we look at that imaginary part, that's the 1 minus iki here. Okay. We can see it's omega over c root epsilon r mu r. Okay. There's the conductivity. 2 omega epsilon r epsilon naught, and you see that the omegas cancel, right? And we see that we can relate the absorption, well this is the wave number for the absorption, is proportional to the conductivity, which kind of makes sense, right? It looks like that. Okay, so I've absorbed the C into that bracket, into that square root, to make it look nicer. Yeah, you can see there's a nice symmetry there. Now, so that's the characteristic wave number for the absorption, which means the characteristic decay length. You can call it the decay length or the damping length, but this is the distance over which the electric field will be attenuated by 1 over E is delta just 1 over the size of Ki, right? And you can see that as the conductivity, this is a bit counterintuitive, isn't it, where the conductivity goes up, which means that it becomes more absorbing. Yeah? So as the conductivity gets better, the decay length gets shorter. Okay, so I've got it we have epsilon naught over mu r, mu naught. Okay. So that's how far our electromagnetic wave will penetrate into a poor conductor like carbon. If I know the conductivity, I can work it out directly. So you should try it out. Try it out for carbon, see how big it is. And the wavelength of that particular frequency, so the interesting thing is how many wavelengths does it penetrate in? Well, the wavelength is equal here to 2 pi c over omega. That's the free space bit, but I have to modify it because of the permittivity and permeability. Remarking one more time that mu r is often 1 and it will often disappear in the formula, as you see. Okay? So hopefully you can convince yourself, since sigma, well, we already said, didn't we, that sigma over epsilon r epsilon naught, that was our condition for the conductivity in the first place. That's much, much less than 1. So therefore, delta over lambda is much, much bigger than 1. Okay? The decay length is much bigger than 1 wavelength. Right? Remembering, of course, this is 2 pi over k here. Okay. So if we draw that pictorially, it looks like this, right? So our electric field falls upon, so assume it's coming from free space, right? So it's the frequency that's the fixed thing here. The frequency is fixed. The electromagnetic wave, let's done it again. Come back. There we go. Don't know what's going on there. Poltergeist, that's all it is poltergeist, isn't it? We'll have to get, what's his name? Oliver Lodgian. He will be the expert for physics and poltergeists. Okay, so the electromagnetic wave has a it's the frequency that's the fixed thing. The electromagnetic wave has a free space wavelength. As it falls upon the surface of our poor conductor, the wavelength is modified and it also starts attenuating. But because of our assumption of it being a poor conductor, we know that the decay takes a large number of wavelengths. So this is the wavelength in the conductor, not the same as the free space wavelength. Okay? It's 2 pi over whatever k was. Remember, k was determined by that dispersion relation. And there will be also some kind of 1 over e decay length. Okay, this is just a cartoon, right? It's not to scale. There will be a 1 over k decay length, delta. That's a skin depth, isn't it? It's how far the radiation will penetrate. Okay, which will be bigger than 1 wavelength, much bigger. Right? So our conclusion is electromagnetic waves do penetrate into a poor conductor. Right? But they are attenuated as a function of depth. Okay? So I'll just remind you, just check that you can do that calculation. Okay? All right. So that's the poor conductor case. Electromagnetic waves do penetrate. And you see that as the conductivity rises, the skin depth should be decreasing. So a good conductor should not have much penetration. That's our intuitive understanding of what we've seen. And that just arises directly. So there's no, not strictly speaking, well, the conductivity is giving rise to the energy absorption, isn't it? But if the conductivity is very, very high, right, we shouldn't expect there to be any energy absorption at all. Electrons are free to move. See what that looks like. So it'll be slightly counterintuitive, but so let's look now. Let's contrast that with our good conductor. Good conductor. This is an age thing. It'll happen to you eventually. Right. So our condition for the good conductors, obviously it's the other way around, isn't it? We're going to ignore those messy situations where they're comparable, aren't we? Yeah, physicists hate doing that. We're going to look at the simple situations only, where we can calculate something. And here it's the other way around. Okay? So this is the opposite way. The way we had before, we had a small complex part and we could use an approximation to work it out. Now the complex part of the expression is big. In fact, it's bigger than the real part. Okay? So K is now dominated by this imaginary term. Okay? So let's look at it. Imaginary term. Remember, this imaginary term is coming from the conductivity. God, it's starting to rain, just ready for Saturday, isn't it? I know this has been a long 5 weeks. It feels like 7, doesn't it, right? We're all ready for a reading week, aren't we? So, and you kind of think, oh, I've done my work now. Especially as third years, right? Third year is hard, isn't it? So here is our wave number again. This is our dispersion relation, and again, you see, we can write it down as the free space bit. This is the bit, the velocity bit, okay? And now all that's left over, because that conductivity term is large enough, we now have that square root there, okay? Right. Now, hold on to your hats. Again, it's all true, but you may have to just see the algebra done a couple of times. I'm going to do a bit of jiggery pokery here. First thing is I'm going to absorb the C one more time, but now I'm going to absorb it on the left-hand side. So let's write that down carefully. I put C inside the square root, and you believe me that it turns out to be epsilon naught sigma omega. Okay, so I'm absorbing C inside the square root. I've got the square root there, and all I'm doing is I'm trying to get rid of this I term and put all the constants of the material on one side and I on the other term. Okay, so if I absorb all those bits into the square root, I get something that looks like that. Okay, that's how it will turn out, and those epsilons cancel. Okay, and on the right, I'm going to write down I in a weird way. So the I stayed inside the square root, and I'm going to write I is e to the I 7 pi by 2 square rooted. Okay. So if you blink for a minute, you will realise, yes, e to the I 7 pi by 2 is minus I. Why has he done that? Okay, because if I take the square root, okay, I can write that as e to the I 7 pi by 4. Just hold that thought for a minute. That's obvious, isn't it, right? On the left-hand side, I've got rid of all my other bits, and you can see here now that I've got what's left is mu r, mu naught, sigma, omega. Okay. So it doesn't depend on the relative permittivity, right? So if you look here, that the epsilon r's cancel, the epsilon naughts cancel from the C, and all I'm left with is mu naught sigma omega, and it's mu r. And again, we remark one more time that mu r is pretty often 1. So in a non-magnetic conductor, it doesn't depend on the permittivity or the permeability. It only depends on the conductivity and on the frequency. Okay? Remember, this is K. This is K that we're writing. Okay? All right? Okay. E to the I 7 pi by 4, I can rewrite that. And again, I encourage you to prove to yourself that this is true. It's 1 minus I. Okay? So we went from a situation where K itself had a real and a complex part. We had a large conductivity, which meant in the expression for K, we only have the complex part square rooted, okay, inside the expression. But then you see that means that the real and imaginary part of K are now equal. Okay? So we can write down K as being, so I've taken that root 2 across now. Okay? You'll see these 2's fly everywhere, don't they? This one goes in here, okay? And we have 1 minus I that goes there. So they're of equal magnitude. And obviously the real bit here, that's the oscillatory part of the motion. Okay? And this is the attenuating, dissipative, or damping part of the motion. Okay? You'll get used to using all 3 of those terms. Right? So now we know that the wavelength, well, and the value delta, the skin depth, are quite close in magnitude. But let's write that down more carefully. So delta, remember, it is equal to 1 over ki. There's no oscillatory bit, right? So that's the 1 over e distance. And obviously that's just equal to 1 over that thing, which is 2 over mu naught mu r sigma omega. I don't know why I put the mu on the right that time. Okay. It's 1 anyway, so it'll disappear when it's so. Okay. And lambda, well, that's 2 pi over kr, the real part. That's the oscillatory bit of the oscillation, and that's obviously therefore 2 pi delta. So now delta is smaller than lambda, not bigger. Okay. So in a poor conductor, the electromagnetic wave penetrates many wavelengths, and here it hardly penetrates even one wavelength. In fact, it penetrates about 1 over 2 pi of a wavelength. Okay? So if we draw that out, it looks different. So we're going to try and draw one wavelength, right? So let's draw, if it wasn't being attenuated, that's like one wavelength. Okay? So this is, again, the same thing's happening. We have an electromagnetic wave of a given frequency omega incident onto the surface of a good conductor. Let's say it's copper, right? And if it wasn't being attenuated, it would have that lambda, but we know that the characteristic attenuation distance, this is delta, okay? Well, that's, you see, 1 over 2 pi, well, it's about 0.16 or so, isn't it? Something like that, okay? It's a lot less, that's the important bit. So our oscillatory bit goes as e to the I k rz, that's the oscillatory bit. The total bit, the amplitude, well, let's draw the imaginary part. The 1 over e, right, that's about 1 over e there, isn't it? Right? Okay, that is the, well, that's basically e to the e to the minus ki z, isn't it? Right. So I'm just going to continue as if I'm multiplying the oscillatory bit with this non-oscillatory bit. So the total is this black line now, and you can see it basically has gone to 0 within one wavelength. Okay, so the magnitude of that bit there, okay, that's the total, must go as e to the minus I 1 minus I k z. Yeah. Okay. Okay. Right. So really, this is a proper skin depth, isn't it? Right? Delta here is called the skin depth, as we call it. It's very important. Let's write it down by swapping omega for the frequency. That's a little more convenient. And we'll swap the conductivity for the resistivity. Okay, this is the bulk resistivity. We can rewrite this, so we can also write it as skin depth. As the resistivity goes up, the skin depth goes up. That's the right way around, isn't it? But most importantly, as the frequency goes up, the skin depth goes down. Okay, so high frequency, so this is for a given lump of metal. If I double the frequency, then the skin depth goes down by 1 over root 2. Okay, so 4 times the frequency is half the skin depth. Okay. So just a note here, rho here is the bulk resistivity. Resistivity, there we go. Okay. That's in omega meters, in case you care. Or sigma is 1 over rho. Just write it down 3 different ways, right? And F is the frequency, yeah, that's right. Okay. Okay. So, in a good conductor, the waves hardly penetrate. Okay, electromagnetic waves hardly penetrate, okay, into our good conductor. And the higher the frequency, the less they penetrate. So we intuitively expect this because, that's our intuitive understanding, just to round off this bit of the discussion. The electromagnetic wave, as it falls upon the conductor, okay, it causes conduction. Right? The electron motion, well, you know, that because there is a conductivity, the electron motion dissipates that. The motion is dissipated into heat, okay, and it's this which causes the waves to decay. Okay. An interesting aside is to think, what about superconductors? Right, I'm not going to discuss them, but I put this as an aside because that is an obvious thing to want to relate to. Okay. Now we've got 5 minutes left. Oh, hello. Yeah.
Sorry, which line is pointing to which?
Oh, I'm sorry. What I'm trying to indicate here is if there was no attenuation, I would be able to draw the electric field inside the conductor using the dotted line, okay? And that therefore the amplitude of the electric field would be oscillatory and it would follow some form e to the I kr, right? When I add on the fact that I'm getting attenuation, the total electric field is equal to the oscillatory part times the damping part, and therefore will fall as e to the minus I 1 minus I kz, so the absorptive bit is these two i's here. Have I got that the right way around? Yes, I have. Yes, because I've got two minuses and I've got two i's, so that's a minus. There we are. Did do it the right way around. Okay, and that k could be either kr or ki, right? It's kr. Okay, so again, the point is that it's just trying to illustrate that the skin depth is much smaller than one wavelength for a good conductor. Okay. Okay. Now we've seen that the wave number in this case, we have a. Remember, this dispersion relation is relating the electric. Is related to how we relate the electric and the magnetic fields together. So we'll do this in a couple of weeks. But maybe if you want to read through the notes on this, but we'll go through it in 2 Mondays. Okay. We should probably remark upon something, because what we've said so far is that in all the things we've seen so far, as an electromagnetic wave propagates through a material or through a vacuum, the electric field and the magnetic field are coupled together. They go up and down in phase. Okay? Here we have a situation where we have a very, very strong absorption, so that may or may not be true. That's the poltergeist again. Okay. So we should probably try to calculate it. So let's calculate, at least we'll start to calculate, the electric and magnetic field in this good conductor. Okay? So what we're going to do is we remind ourselves that it's E and B together, isn't it, that makes an EM wave. Okay? And they together must satisfy Maxwell's equations. Maxwell's equations. Okay. So we previously said, didn't we, that E is equal to E0 e to the I omega t minus kz, whatever omega and k are, and B separately has a similar form, e to the I omega t minus kz. Okay. And we remember that del cross E equals minus dB by dt, dB by dt, okay? That's how the two fields couple together in general. So therefore we have K cross E0, that's the direction, including the direction, is equal to omega B0. That's where we got our relationship between the relative strengths of the electric and magnetic field in free space. The magnitude of K over omega is C, isn't it? So the two fields are quite different in magnitude. Okay, so we can rearrange that. Okay, cross E0. Okay, and we already saw that. Right. So we're going to leave you with a simple statement, right? When K was real, okay, then we have the situation that B0 is perpendicular to E0 and is perpendicular to the direction of propagation k. And we also see that they're all in phase. Okay? But now k is complex, and it's complex enough, isn't it? The complex part is equal. The magnitude of the complex bit is equal to the real part. So I should put if. Yeah. If k is complex, then that's not true. Okay? B naught, write it out a bit laboriously, B naught is not perpendicular to E naught, is not perpendicular to k. Okay? So that's in a conductor. So this is our dielectric case, of course, when k is real. And here, this is our case in a conductor. Okay? So clearly there must be a complex phase relationship between E and B. There is a phase difference between them. They're not going up and down together anymore. And the phase angle difference is tan phi equals ki over kr. Okay? Phi is the phase between the oscillations of E and the oscillations of B. Okay? And we'll leave it there for today. Okay, so we'll calculate those phases directly next time, and you can already see what's happening in a good conductor. It's going to be 45 degrees. Right, so I'll see you in 2 Mondays. Hello, where have I? Oh, sure, okay. Yeah, let's have a look. Let's pop that down. What's the question? Oh, okay. That is a little bit of a cheat. What we're saying is, okay, we're saying that, we're saying here that J, the general form of the magnetic vector potential, is given by an arrangement of currents. We replace this arrangement of currents saying that, firstly, this is the time variation, e to the I omega t, that's fine, yeah? This is the phase thing, e to the I k r, that's fine. The important thing is how big J is and where it is. So we're saying that I0L is how much current is moving over what size of distance, yeah? And it only occurs if r equals 0. So r prime is 0. So all we get is that. Okay, and it's only moving in this direction z. So the vector part of this is that z there. Okay. Yeah. I naught and L is the amount of current flowing over an amount of distance. I know it's a fiddly concept to think about, where we're replacing this integral with a certain amount of current moving that way. Okay? Does that make sense? Yeah, okay. Hi. Sorry, you must be next, obviously. Yeah. Hello, mate. I've seen you before. Which department are you in? Biology. Oh. We're not supposed to talk then, are we?
Physics.
Yeah. You see that? There we are. Enough said.
I heard current moving, so.
Yeah. I think it was Galvani who did the combination of those two things, and nothing good came out of it. Right. Thank you. You too. Thank you.